Okay, hello everyone. So I'm a third-year PhD student working at the National Observatory of Athens, and I'm going to talk about the mass loss of red supergiants, which is, as you also saw in previous talks, an open issue. Starting with a brief introduction on red supergiants, you already had some in the previous talks. So they're evolved massive stars in the range of 8 to 30 initial solar masses. And they are cool, occupying the top right corner of the HR diagram. So about the mass loss now, we know from the literature that it ranges from 10 to the -8 up to 10 to the -3 solar masses per year. And you see that this range is huge, and we're going to discuss about why it is like that. And defining a mass loss rate, a robust mass loss rate, is important because it can have implications in stellar evolution models and the type, and this can affect also the type of the resulting supernova if we have really high mass loss rates, and it can strip off the envelope of the star. And it can be suggested also as a solution to the red supergiant problem, which is the lack of high mass red supergiant progenitors of the supernovas. Let's see this scheme of the mass loss mechanism, which is still, the theory behind it is still unknown. So we know that red supergiants are pulsating. However, these pulsations are not considered enough to lift off the gas outside of the gravitational potential of the red supergiant. Then we have a missing force that is suggested to be the turbulent pressure in the atmosphere and the inner wind of the star, which can drive off with a constant velocity the gas up to a higher radii where dust can be formed. And then maybe we can have some radiation pressure on these newly formed dust molecules, which will enhance this mechanism. Then some other implications of the red supergiants is that we know that they form different elements in different burning phases, and they end up with an iron core and collapsing with a core collapse supernova, which contributes to a chemical enrichment of galaxies. So let's go. We have seen also, we have discussed about this zoo of mass loss relations. Now on the right, you can see the mass loss rate versus the luminosity by work by Yang et al., which our group was also involved in the SMC, one of the largest samples studied till then. And you see that all the other lines are different relations that can have a discrepancy by 2 to 3 orders of magnitude. And this is because they are studies in different galaxies, meaning different metallicities, which we don't know how it affects mass loss in red supergiants. Then different sample sizes, most of them are small sample sizes. We are talking about tens of red supergiants. And most importantly is the different assumptions that, as we can see, can lead to much different results. With orange here, I denote the most commonly used relations in stellar evolution models, which is the de Jager one. But this relation is derived in the 80s, and it's a study of only 15 red supergiants. And I have to mention that most of these relations are empirically derived based on the dust cell properties, which can give many uncertainties. So I'm starting this presentation now of our results with a recent publication of the mass loss rates in the Large Magellanic Cloud. We gathered the sample from 3 different catalogs based on photometrically selected red supergiants by color magnitude diagrams. And we know that they occupy this, the red part as denoted in this plot. And combining these catalogs, we end up in around 2,000 red supergiant candidates after also cleaning and applying some constraints to our sample. So then we use the radiative transfer code DUSTY Assuming also steady state winds with a constant outflow velocity. And what it does is we have as an input the stellar spectrum, and then it solves the radiative transfer equation of the dust cell, assuming a spherically symmetric cell. And we get as an output this doesn't work now. Yeah, we get the emerging flux, and then we can, deriving the properties of the dust cell, we can estimate its mass, and then assuming a gas-to-dust ratio, we can find the mass loss from the star. Here are all the input parameters. I'm not going into details. The optical depth is the most significant one, which shows the thickness of the cell. So then we proceeded with the ACD fitting. We gathered photometry from different surveys from the UV to mid-infrared. And here the orange points are the observations, and then the black line is the best fit model, and all the other lines are the components of contributing to the flux. So the most important part is the mid-infrared part, which the infrared excess shows the property it's due to the dust emission from the cell. And then we found out that we have also some sources in our sample which didn't show any infrared excess, and they were fitted with a lower optical depth of our grid. And these are not dusty Red Supergiants, and we use them as upper limits. Next one. So this is our main result, Mussel's rate versus the luminosity. With color, you can see the optical depth, meaning that the green, yellowish colors are the more dusty targets, and the gray triangles are these upper limits, which is not a negligible fraction. The red star is an extreme Red Supergiant WH-G64, which is a kind of weird case, and as you can see, most of the Mussel's rates are quite low. And also the circles denote the spectroscopic Red Supergiants. What is interesting also here is the kink that you observe in around 4.4 in luminosity, showing an enhancement of mass loss, which needs to be investigated further. Next one. So we found also similar rates. There was also a similar work in the LMC some months before ours. And yeah, again. So investigating this kink, we have this diagram, the median absolute deviation of WISE1 band, around 3.5 micron, which it shows the intrinsic variability of the star. So we see, let's say, the variability versus the luminosity, and we find that also there is a kink at the same position. So variability and mass loss are correlated. And then we investigated using different assumptions. So if we use the radiatively driven winds as the dominant mechanism of mass loss, then with orange, you see that we found higher mass loss rates by 2 to 3 orders of magnitude. But Red Supergiants are not considered to have this mechanism as the AGB stars, because as it mentions also in the previous talks, they have much higher radii and hotter temperatures, then dust should be forming much higher radii. Next one. And we also saw that this can be unrealistically high mass loss rates. Next. And we did this investigation in order to properly compare with other works, because usually people see all these lines, but they don't know why they are different. So now, as you can see here, the Yang et al. And the Van Loon and Goldman, 2017, those that are high, is because they assumed radiatively driven winds, mainly because of that, as they're in their models. And then we find slightly lower rates than the de Jager prescription, and mostly similar with Bezoar, which we had similar assumptions also, and this relation was also an initial mass-dependent relation. And similar, let's say, to the first theoretical attempt by K 2021. Let's go to the next one. And also there was a recent paper, again, deriving an analytical prescription by Fuller And now we find similar rates to that, at least for high luminosities. Next one. And then we established a relation, both dependent on the luminosity and the effective temperature. Now on the right, you can see that the mass flow rate versus the temperature, and you see that there is an anti-correlation between them, which has been also shown in the past and is expected because lower temperatures we have our red supergiants in more evolved states. And then on the left, you can see applying a relation with magenta points, you can see the prediction. And this dependence of the temperatures partly accounts for also the dispersion in the results. Next one. So, okay, we had this work on the LMC, and we sent that we need to examine if metallicity affects the mass loss rate. So we went to other galaxies using similar assumptions so that we can uniformly compare the results. Next one. So we started with the SMC, even though there was a work, but we need now to use similar assumptions. And here we find similar rates, though now you can see that the kink is shifted to higher luminosity around 4.6, which can be due to the metallicity effect, maybe because in different metallicities we have also, for the same initial mass, different luminosity. Next one. And then the kink has been also shown that it's correlated again with variability. Next one. Again, we find a similar anti-correlation with the effective temperature. Next. Then we proceeded with NGC 6822, which is similar metallicity with the SMC, although here the results are more uncertain because the mid-infrared photometry is not as good because it's a more distant galaxy, apart from the orange circles, which is where we used JWST photometry. However, these are only for low luminosity sources, and we can barely maybe see that there is a kink around 4.6. Next one. Then we got a sample from spectroscopic red supergiants in the Milky Way. Next one. And here we find slightly lower rates, although again here the results are slightly uncertain because you have uncertainties in the distances of the stars in the Milky Way, and also depending where you look in the galaxy, you have different interstellar extinction which can affect the results. Next one. And here we don't observe any kink, which is interesting. So also we don't see any enhancement in the variability. Next. Gathering all the galaxies together, you can see that the rates are similar, slightly lower for the Milky Way, but more uncertain. And the different position of the kink between SMC and LMC. Next. Also here I denote, I have with red some results from a galactic red supergiants by the SIN 2024, which is derived with a different method from gas diagnostics, which are in agreement with our results. Then we can say that comparing with different methods that our results are, let's say, more robust. And next one. And all in all, we have gathered studied the largest sample of red supergiants in different metallicity environments. We found this kink which shows an enhancement of mass loss and needs to be investigated more. And we can say that we don't find any strong correlation with metallicity, although further investigation is needed. Next. And for this, we can go to different galaxies and metallicity environments when we have JWST photometry. And non-dust dependent methods also can, comparing our results, can give us more hints of how well they are. And about the kink now, a good way to see if it's physical is to examine to have measurements of turbulent velocities and to check the relation with the luminosity, and if we find kink there. And then the question is it real? Maybe it's due to AGB contamination, and if we remove the AGB stars, then we could see a straight line. And yeah, next one, this is our group, and I would like to thank you.
Thank you. A very nice talk. I have a curiosity. Perhaps you tell me if I'm wrong. But as far as I understood, you derive the mass loss rate from the fit to the SID. So you are deriving the dust mass loss rate, and you need to assume some dust to gas mass ratio, no? Is that correct?
Yeah.
And what is inside that? I mean, what do you assume, and does it affect to the errors in the determination of the mass loss rates?
Yeah, it does affect, because we assume one average gas to dust ratio in its galaxy, which, I mean, for the case of the LMC, it doesn't vary that much, and it's linearly dependent. So in log scale, you won't see much difference. Although in the SMC, it varies quite a lot, and then you can have more uncertainties.
But which value do you adopt?
Which value?
Yeah.
For the LMC, we use a gas to dust ratio of 250, 300 around, and for the SMC around 1,000, 1,200.
Okay, thanks.